Yeah, no, it's great to be here. I did the summer school in 2019 for the first time, and I think I was the only one working on machine learning at that time, at least from the group. And so it's great that there's an entire summer school centered around that topic now. So that's really, really amazing. Okay, so for this presentation, I will talk about the applications of what you just heard, applications of discriminative models, and also about emerging topics. So I will structure it like this, that we have like the first half, a bit more than the first half, basically on actual applications to review how different challenges are tackled in heliophysics with machine learning. And then the second part will be like new concepts, where we actually have a deeper look into like a new concept, which is about physics-informed machine learning. Okay, so we have a couple of goals that we want to achieve by doing this lecture here. And that is basically to understand why we want machine learning, where the advantages are, and how we can actually use it. So what I want to do first is basically to build like we understand basically how we can address heliophysics challenges with machine learning, what the advantages are, and also basically not only to understand the challenges that we're trying to solve, but also how to frame it properly in a machine learning framework. Because this is kind of like the important thing that you need to do in order to translate your scientific question to something that you can solve with a machine learning tool. And then also basically to not just reframe it, but also identify how you can solve this task afterwards with the appropriate tool. And we'll do this by basically discussing this here. So we'll try to make this like an open discussion, but also having a look at the literature, how this is done by recent approaches. And also, we don't want to, like, as said earlier, it's not all nice and good. So there are also like limits, and we also want to identify those limits, and we want to see where the downsides are, and when it's better to actually go for something simpler rather than going for something more complicated. And then the last part of the lecture will be about physics-based losses, hybrid approaches, and how we can basically use AI methods for data-driven simulations. Okay, so let me start with this. So from my perspective, in terms of big challenges that we have in heliophysics, like in general, are like that can be addressed by machine learning methods, fall into like these three categories. So we have observational challenges, we have the physical challenges that we are facing, and we have operational needs that we need to satisfy. So in terms of observational challenges, like one of the big aspects that always comes into play when we think about machine learning methods in heliophysics is about the high data volume that we have. So we have observations from multiple different instruments. We have remote sensing data, filtrograms, spectrographic data. We have in situ measurements, and we cover like a wide range of the spectral band. So it's an incredibly large amount of data that we actually obtain like all of the time. So it's like way more data than we can analyze just with the workforce that we have. So we need automatic methods to address this. On the other hand, it's too little data. So actually what we observe is kind of like just a fraction. And all of the observations that we obtain are just like a representation or like a certain measurement of what's actually going on the sun. So while other disciplines can maybe go to like a certain place and do the measurement there, we can't really do that, right? We can't just fly a probe into the sun and measure the magnetic field there, for example. And one good example for this is this image that you can see here at the bottom, which shows this CME eruption, where we have the EOV observations at the center, and then we have coronographic data going further out. So basically, this shows us how the plasma is being ejected and moved out throughout the heliosphere. But what are we actually seeing here? So it's like 2D imaging data, right? But actually what we see is like a full line of sight integration. So it's a 3-dimensional structure that we're observing, but we only have a 2D image of this. There's a whole part of this missing. And what we only see, like for example, in EUV observations, is also just a fraction of the spectrum. One part, like one specific temperature range of the solar corona. So it covers only like a fraction of what we actually have on the sun. So this is also like a big missing piece, is kind of to fill like these gaps in. And on the other hand, also like thinking about coronal ejections, for example, those are complex processes. So we have multi-scale processes that are happening, highly nonlinear processes that are happening, and they also coupled across the entire system, ranging from the sun through interplanetary space and to geospace. And ultimately, one of the big, so this is kind of like a key challenge that we also addressed, to actually have models that provide like a certain amount of complexity that can match the complexity of the actual physics that we observe. And then lastly, operational needs. And that's kind of straightforward here, because we have space weather forecasting mitigation, where we actually want to have tools that can give us like pretty straightforward warnings and information about potential space weather impacts. And also in talking about like big data here, we have a lot of data coming in that needs to be processed, and a lot of this processing is like highly complex, and we want to do this ideally in real time. So let's just take one step back and see again what tools do we have available to actually address these tasks. And like this presentation is primarily about supervised training, so we'll focus here only on the supervised aspects, and you will hear later on more about different approaches on how to tackle this with unsupervised training or generative models. But the basic principle here, and this is kind of what we are focusing on right now, is like, just to break it down, is kind of what we are trying to do is find a mapping between inputs and outputs. And this is kind of the primary challenge that we face, is when we have our tasks, that we translate them to something where we can have a certain input and an output. And for machine learning methods, it's the idea here is to use relatively simple functions to find like a function mapping. And going to deep neural networks, we can basically make use of this concept that we can generate arbitrary complex functions. So this is a mathematical theorem where this was basically shown that we can approximate arbitrary complex functions with a neural network, as long as we have enough free parameters available. And this even applies to like the very simplest form, where we have just like one layer of neurons that are basically stacked together, and which can basically perform this mapping for us. So in practice, this is like more sophisticated and the design matters. But for this presentation, I want to focus rather on the application side. And the important part that we want to that we should think about here is basically to have a neural network just as a function mapping. So having an input and an output, and then using this arbitrary complex function to basically find the mapping between these inputs and the outputs. And this is all enabled by basically having this general concept of a neuron, as we heard earlier. So it's just free parameters that we have that we can adjust, and that can give us the complexity that is needed to achieve this mapping. Okay, so as I was saying, it's like in principle, we can approximate arbitrary complex functions with a neural network, but there's one downside with it, especially when we do this in supervised training, and that is, we can only find an appropriate mapping if we have a large enough data set available. Otherwise, the model will just collapse. So you've seen this earlier. Basically, with the comparison, this is like a very good analogy where we have like a linear regression and then a polynomial fit. And the same thing happens like for problems that are also higher dimensional. If we don't have enough data for the actual fit, but a too complex model will just overfit to a specific data. So having for supervised training, having a large amount of data is actually a pre-requirement, and one of the biggest downsides, and one of the things that's usually the hardest to achieve. But one of the primary examples and one of the biggest successes of deep learning approaches at the beginning was definitely classification. And that really illustrates like the power of this approach. Because if you look at like those images here on the right-hand side, sorry. Yep. Those images here on the right-hand side, or even like the numbers up here. If you would think about writing an algorithm for this, to basically frame this into like a software that you're writing, right? To identify the classes, how would you even start this? It's like super easy for us to describe what's in this image, but like writing this down into like a piece of code, for example, or even describing how to identify individual images is very difficult. And this is actually where this comes into play. We know the mapping, we know the inputs, we know the outputs, but we don't know the function in between. And this is actually exactly where we can use these complex mapping functions in terms of neural networks, where we can basically take this image like as an input that goes into the neural network, and the output is just a classification. And then we have a large data set that we use to learn this function mapping in between. And as you can see here, those are not heliophysics applications, but they are relevant for heliophysics. And most of the things that are happening in computer science right now have a direct application to heliophysics. So we can directly profit from the recent developments and make use of this for our applications. So let's have a short look at what actual opportunities are that we have, how we can actually address like challenges that we have right now in heliophysics. And then we go to some examples. So in terms of advantages, we have, like what I was mentioning before, is kind of the large amount of data that we need to process, the real-time demand, and this is like one of the key strengths, and it's like primarily highlighted for most of the applications, is that deep neural networks are very computationally efficient once it's about the inference time. So the training can be longer, but the inference time is typically very short. And that even applies to very complex tasks, like for image classification. It's not a long processing step, but usually you get your results within milliseconds. And then also when we compare this and think about classical approaches, how we do this, we can see that by having this flexibility of basically defining our input in an arbitrary way, we can make really use of the multidimensionality of the data. And you can see this, for example, here from these solar observations, from the photosphere to the corona. All of these features are related. But it's for writing a classical algorithm for this is very complex to combine this information. But for neural networks, it's a straightforward application just to use like all of these channels simultaneously as an input in order to have more information about the underlying data and the relations between the features. So as said, we can learn complex patterns because we have arbitrary complex functions. So as long as we have enough data to train, we can actually find a mapping no matter how complex the problem is in theory, okay? On the other hand, it's also like the results, especially for classification tasks, those are probabilistic outputs that we get. And that means basically we always have a certain amount of uncertainty estimation included into these methods. So in contrast to other methods, just give you like a yes or no answer, basically, neural networks have also like an inherently probabilistic characteristic to it, or machine learning methods in general. And in most cases, for the training, you need a data set. So also for the evaluation and testing, it's usually applied already to a data set. So it's kind of most of the methods that we see are kind of already well tested once they are deployed, especially when we compare this to classical approaches that make like case studies and show that the method works for certain examples. Neural networks and machine learning approaches are in general always evaluated on like a large statistical data set. Yeah, but there are also shortcomings. So we need this large amount of data, and like one of the biggest criticisms is we basically lack the physical understanding, especially if we rely on data and use only data for training. We face this problem that we lose basically the grasp on the physics. But on the other hand, like when we develop methods and we want to classify features or anything in this direction, we also want to obtain ultimately a better understanding of the underlying physics. So this is like a core problem, right? So basically to open up this black box is one of the key challenges for machine learning in heliophysics here. And we'll go through some applications where the applications that I'll try to highlight actively address this challenge to also have like not only like a good performance, but also to have a better physical understanding into them. Okay, and the last part, maybe a wild statement, but I put here, training machine learning models is not hard. I probably should say it's not as hard as the rest. It can be also very difficult, but usually the tricky part is to define the task right and to prepare the data in an appropriate way. And this is what we're going to do next. So let me jump over this. Right. So for the next part, we'll go through some of the active problems and challenges, and we can have an open discussion basically on how best to approach this with what you have learned so far. And I just want to review here basically our toolbox that we have in terms of machine learning applications. So you've heard about classification, regression. I think you haven't heard too much about segmentation. And then I also have defined here data transformation. So I just made like those 4 more arbitrary classes kind of. So classification and regression is kind of clear, right? For a classification task, we basically try to approximate a function that takes inputs. Like for example, here we have an x values and y values. And then we want to predict a probability, so ranging between values between 0 and 1, for example, that gives us, that can classify those dots based on their location in terms of the features that we put in, x and y. For regression, we basically have an input x, so we learn a function f from x that maps x to y. So we basically just have a smooth parameter output like open. So it's like a variable output that we have. And basically the extension of this would be segmentation. So you heard about convolutional neural networks. So the idea here for segmentation is what you can see down here. Once we have an image, we want to basically classify each pixel. So instead of having as an output like a single value, we can also make the output arbitrary complex. So what we can do is we can basically define each pixel gets a certain classification assigned, and we do this over the whole image. So this would be a segmentation task. And the last part is basically data transformation, which would be very similar to, we have some input, we get an output value, but the way it's meant here is kind of in a more complex way, so that we actually map, for example, one image to another image in that setting. Okay? And the data that we're dealing with are time series images. We can have video sequences and or extracted features. And this really shows the flexibility of these approaches, because we can basically treat this always in the same pattern. Just use some sort of input data, which represents the information that goes in. And then we have a certain output task that we want to optimize this for. Okay, and we still have like the corresponding models to solve those tasks actively in the end, where we have like classical approaches, which would just do image processing. We have machine learning approaches in terms of support vector machine, random forest, for example. So you heard about support vector machine before. But then also deep neural networks, which serve as this general function approximator, convolutional neural networks, which are used for imaging data, and transformers weren't covered so far, but we'll also not use them here now. Okay. So let's jump into some actual applications of heliophysics problems. And I thought a good starting point for this is like a problem that's like long-standing, which is about solar wind and solar wind forecasting. So this is kind of a really good application for machine learning because we're interested in forecasting these events. And this has been already done previously by the community as well. So we have multiple goals basically here. So what you can see on the right-hand side is basically data that is observed by, that is provided by Omni, where we have solar wind density, speed should be also here, yeah, this is the red one here, pressure, the DC, and then also the geomagnetic indices down here. So the question here is now, in terms of, what do you think, let's focus for now on forecasting. What would be the best way, what should we address, what should we predict, and what is the best way to do this actually? Is this a classification problem? Is this a regression problem, segmentation? Are we data transforming, or is this modeling that we're doing? And just to get us started, maybe we can scan this QR code up here, and we can make this a short poll where people can basically input their thoughts. And you can pick any number of those challenges. So I only put in the, I only plugged in here the last part to how to address the challenge, and then we can discuss this further. Oh, I'm sorry, maybe I can zoom in here. Maybe, no, probably I would need to. some mouse or so. Okay, but answers are coming in. Okay, so we have right now, majority goes for modeling and simulation to actually address this. We have a few classifications and we have regression pretty much on the same level. Anyone want to elaborate on why they think modeling and simulation would be the best way to approach this? So you probably already had like a lecture where you were using heliospheric models. So from that perspective, it makes absolute sense, right? To have like a sophisticated model that can actually produce the solar wind everywhere in the heliosphere. But maybe if we think about forecasting, we are only interested in a single point, and maybe using there some relations is pretty straightforward. So the majority went for modeling and simulation. I didn't put the example here because I wanted to focus on machine learning, but of course, those are like the established models that actually estimate the solar wind everywhere in the heliosphere. But the accuracy can vary, and it's not, and maybe it's also not able to capture like the full physics, while maybe a data-driven approach can capture more of the underlying phenomena. But any idea what would be like the easiest approach? Like what is the easiest way if we would be sitting at Earth to forecast the solar wind speed? Like from that point, right? Any ideas? Like it's a very simple, like it's like in terms of baseline models, you have a few choices, right? And what is like an easy way to do this? Yes? Right, that's a persistence model, and that's a great first approach. And that's like a really good baseline to have. So just the wind stays as it is, right? And you just predict it will just continue what it's doing. And for the sun, we actually have one more aspect that we can use about what we know about the sun. Any ideas? Sun is rotating, right? So what is causing the solar wind? Like the features that we observe that basically spill out the solar wind. And the sun is kind of like not evolving too much, right? So there should be some correlation. So any ideas how we can basically forecast the solar wind by just using that? Coronal holes we go into next, but the idea here is really just use the wind like from this previous solar rotation, and you just add it, right? And that's already a good approximation. It works in many cases. So basically this tells us already kind of what needs to go in. And then coronal holes. Coronal holes are also a great idea. And this is kind of also what we see in terms of what we can do in terms of physical modeling. So where we have basically coronal hole maps. So this is like an application, like a classical application, and you can just see basically how they relate the area of the coronal holes to the solar wind speed. And there's actually a pretty good correlation here already. And this doesn't require any additional learning. Just using like the area of the coronal holes, a scaling parameter in between, and that gives you already the solar wind speed. Because the coronal holes are actually what is causing high solar wind speeds, wind streams, and therefore this works pretty well for this application. So how can we frame this with a machine learning aspect? So people were also going to have like a tie between classification and regression, and both are correct, and both were done in the past. Does anyone want to elaborate on regression, how we could use that? What would go in for the regression? What would go out of the regression? Solar wind speed, right? Yeah. And the input, what could be the input? We need some information. Like where's the solar wind coming from? What is producing the solar wind? Yeah, like the sun in general. So maybe a good input could be the sun, right? The sun as an image. There are approaches where basically people were using like solar wind as an input, but how do you know what is coming up next, right? You don't see any, there's nothing that tells you what is coming towards you. But there are approaches that actually use solar images as an input and predict correspondingly the output. And this is basically building on the very same concept as the other methods that use like previous solar rotations or coronal holes. But now they can also take into account not only the coronal holes, but also like active regions and the general state of the EUV corona. So this is, those are two papers. that use basically also an approach where both of them use UV images as an input, but they also have an attention mechanism coupled to it. So this will tell us basically where the network is looking. And those are some applications where you can see where the network is, which region the network identifies as relevant. And you can immediately see here, this is the coronal hole. And down here, you can see those are the two coronal holes. And when we compare this in terms of the forecasted solar wind, we can see that this is a pretty good match, better than what we have with a classical approach where we just use active coronal hole area as an input. Right, and yeah. Sorry? Those are just, those are the inputs. Basically, they take 4 images as an input. Yeah. Oh, that's just the second example. It's from a different time sequence. Yeah. Oh, the attention. The attention is basically obtained after the training, and which basically is like a back tracing through the network, which highlights areas that are of interest to the neural network. So it's a really nice application where you can actually see that we can lift the black box and look into what is going on. Okay, and can you see what's going on down here? Probably that's very hard to read. But any speculations, what could be the difference between this really good match here and this one here where we don't have a match at all? Any solar wind experts here in the room who wants to take a wild guess? It's all solar wind speed over time from different dates. Right, perfect, yeah, great. It's a CME. And why is the model not capturing the CME that is coming in? It's not in the data, right? Maybe it sees like at some point the CME that is being launched, but it probably wasn't in the data set that the model was using for the learning. So it's a pretty nice example that shows that the model is performing bad for that case, but we actually want that because otherwise the model would drain information from somewhere. But in this case, it only uses information from what it has available. And then we were also talking about classification. So this is one example where people labeled basically the solar wind speed into different source regions and then applied the neural network for exactly that case. And you can see that this is a task that requires really human interaction. So you would need to sit down and label your wind data. But they basically did this for a certain data set, trained the neural network, and can apply this now throughout the entire data series. So providing basically like fully classified solar wind speeds. And this same thing down here, and this looks even worse because this is the magnetic field strength, and those are observations of coronal mass ejections observed in situ measurements. And you can see that like those are like only tiny variations, and it's even for experts hard to identify ICMEs in the observational data. But here they trained a deep neural network for this case to actually provide like class labels for the individual regions. So basically what goes in is like the time sequence, and what goes out is a sequence of classifications. So it's kind of a segmentation task, kind of a classification task in that sense. So it's a 1D segmentation if you want to see it like that. Right, but also we were also talking about other parts of classification. So especially when we go back basically to the data that we have, we can see that we have kind of good agreement that this is kind of like solar wind speeds are probably like easier to estimate because we have like the direct relation to structures. But on the other hand, like having like BC or the geomagnetic indices are much more difficult to capture. So what people do instead of like predicting the actual values is they treat it as a classification task, which usually performs better and gives you like a probabilistic estimate of how likely this event is to occur. And here they were also using observational data, but now actually including information about CMEs by using LASCO, chronographic data, and then providing a probabilistic forecast based on basically taking in a sequence of images and then providing as an output a sequence of forecast of DST indices, like a probability that the DST index falls below 100, minus 100 nanoteslas. Exactly. You can think about it in multiple ways. Of course, you could match one image to one point in your solar wind speed, for example, right? So this would be like one image corresponds to this. You would take like the exact point in time that corresponds to this. What the authors were doing here was basically to take like a sequence of 4 images, and then they defined like a forecasting horizon. So basically they take in like a short video sequence, if you want to call it like this, like 4 images basically. And then as an output, you would have like the solar wind speed values over like the forecasting horizon. So it will predict like the entire time sequence for this case. So, but yeah, that's kind of like the flexibility that you have in defining the task in the first place. Maybe it's a good point to ask here as well, what prevents us from actually doing much more forecasting, much longer time sequences? What is like the issue that we face when we try to do much more? Because in principle, neural networks are arbitrary complex mapping functions, so they could map anything, right? But if the data is not there and the task is not well defined, we probably won't find a solution. So it's like a critical point to define the task right in the first place, to provide the necessary information, because otherwise we'll see exactly this will happen, right? If the information is not present, the model will fail. And in the worst case, the model wouldn't learn at all, because if all the examples would be CMEs and the data isn't there, the model would never learn anything. Nick, how much time do we have? Sorry, 1 second. How long are we going with the lecture? Just that I can track them. Perfect. Okay. Sounds good. Yeah. Mm. Mm-hmm. You mean in terms of like, yeah. I see what you mean. Kind of like the how to define the forecasting horizon, right? Mm-hmm. Right. I mean, like the usual strategy is just to define like a kind of long time frame, like from the first point where we expect that solar wind streams would be noticeable, and then we would have like a natural lower performance like towards the beginning and towards the end, where like the speed can vary, right? But the idea is kind of to capture always like the center. And the way that it's applied in the end, like also for these applications here, it's kind of a running window, right? You would have this like in an operational setting, you would have your image sequence running in, and you would have your model running over this. And then you would basically take only like the central part where you have a high confidence, or like take an average of all the model results that are accumulated over time during that frame. So you would essentially skip those regions. You would still try to forecast like towards those parts, but also kind of like expected to perform worse. So you would only focus like on the central parts kind of the time sequence where you have a good agreement in terms of solar wind speeds and what you have in your model forecasts. Yeah, great question, yeah. Okay, sorry. Yeah, and that was, yeah, maybe let's have a quick look at this one here as well. So basically, this is just that you see, like I was planning basically to skip the entire technical aspects, because I was saying training machine learning models is not the hardest part. Defining the task is the hardest part, right? But it's also worth to think about, like, once you get started with the task and you have it well defined, you also need to think about the architecture. And here you can see basically how this is done for a case like this. You can also see like how this is processed. Because for now we were mostly thinking about like just taking like a video sequence, put it into like stack it into the neural network, and then the output is just a solar wind. But usually you can see that there's more to it, where we have basically here the sequence. We have separate networks that extract features from this. And then those features are fed together with like a time information. So from each image, basically features are extracted. Then the features are correlated across time. And then those features go back out. And then this network here basically takes care of transforming this into the corresponding output shape. So it's more like an architecture design choice how to do this. And there are multiple different ways to do this. And I just wanted to note here, basically, it's interesting to just check the literature on how this is like done like with the current state-of-the-art methods in that way. But in principle, we can focus for our task that we're defining here on just what is the input, what is the output, because this is like the primary criteria for all of them. And then it's mostly about which model to choose. Okay, so we were talking about coronal holes for solar wind speed, but what about identifying the coronal holes in the first place? And of course, coronal holes are a signature of the solar magnetic field. So they represent regions where we have open magnetic field lines. They are really important for forecasting solar wind speeds, right? We just had that. And in particular, because they produce the fast solar wind speed, which can have adverse space weather effects. But also in terms of thinking about the open magnetic flux problem, they play an important role because they're a signature of the magnetic field. So we want to understand, or basically we have to know where are coronal holes, where they're located, and how do they evolve over the solar cycle. So a good machine learning application for this would be, for example, to identify the coronal holes and detect them. Okay, so let's repeat the exercise from before, and I'll swap to the next slide here. Let's see. Does this work for you? Should be switched now to coronal holes. And we get the quick poll running. So what would be the best way to extract where coronal holes are located? Would this be a classification task? Would this be a regression task? Is this image segmentation? Is it a transformation that we should do? It's kind of loosely defined. Or should we use modeling for this? And the good part about this one, there's no wrong answer, because all of these approaches have been applied to this exact problem. There's a variety of different approaches for this. Okay, well, yeah, that's a pretty big chunk for segmentation. Yeah, 17 people say segmentation. What is nice about segmentation? Anyone wants to say anything about it? Any ideas? What is like the good, what is like the advantage of segmentation over classification, for example? Maybe let's have a look at the data first, and you tell me later what was the nice thing about having segmentation over like a classification, okay? Okay, image segmentation. That's like one of the big applications, and there are so many models that there are even statistical studies over what the models do, right? One of the downsides, of course, that we have with this, with the image segmentation problem, is we need first like a clean labeled data set. But in principle, we can apply this immediately. We can take these images as an input, and then let each pixel be classified as either like a background, quiet sun, or other structure, or the coronal hole itself. But there are also other approaches. For example, like a combined approach, or like classical approaches. So let's review this first. So one of the easiest way to approach this is kind of to use just the thresholding. Coronal holes appear dark, right? So what we can do, like the easiest approach, and that was done, like everything that was done before, builds on like just use a threshold, say all the dark pixels are coronal holes. So that might not be the best choice because there are also other dark parts. So people started introducing clustering to basically eliminate like smaller dark spots in the images. And that gives you like the larger regions only. Any idea what could be the problem when we do this with our imaging data? If we just take the data, apply a threshold, and then cluster it into the bigger regions. Do you think we detect all the coronal holes, or could there be a confusion with anything else? Yes. Exactly. This is what you see down here. A nice elongated filament. And it's automatically identified. They also appear dark, but it's a very different magnetic structure. So from that perspective, we really need to exclude them. So for everyone who was saying classification, for example, that's what the people in this paper here did. They basically did exactly this: clustering, thresholding, clustering, and then taking like the images and extracting features, length, width, magnitude of the intensity, and so on. So extract a couple of features, and then you can just use this as input, like for example, to the support vector machine. And then predict from this, classify it just as coronal hole or as filament. So the only effort that you need to do for this is actually not to develop like your own labels or pixel-wise classify the images, but you just need to apply your thresholding algorithm, then manually go through the data set, say which of those are filaments, which of those are coronal holes, and then you have your labeled data set that you can train with. But on the other hand, it would be probably better to actually use like coronal hole masks that actually give you something that looks like this, right? Where you have actually like a segmentation, and it can also avoid filaments that are in the observations. Because yeah, so but what you can see up here is basically from this comparison study where all the different segmentation models were used. There are a lot of classical approaches, like different approaches from classical computer vision, but there are also like two machine learning approaches involved, or like deep learning image segmentation problems involved. And you can clearly identify them, right? Because they are the best performing ones. No, right? It's like really hard to say which one is doing better, which one is doing worse. There's no clear identification, and it all comes down to the labels. And this is actually what we also see for the observations. It's kind of, when we don't have a clear answer to the task that we're trying to solve, we will be stuck somewhere in between. So the model will only be as good as our labeled data. And if the labeled data is incomplete or is not correct, then we also the model will not learn it. And this is actually also the case here for these machine learning approaches, because they also use a labeled data set, and all of these labeled data sets have certain errors, because it's impossible to capture like every single pixel correctly, because it's also for human observers really difficult to identify coronal holes reliably. But one interesting application, so this is one of my papers on this subject, and which is basically the idea of using neural networks in a different way. So while classical methods usually use only one channel, what we can use with deep neural networks is basically the full combined set of channels. And this is really powerful because we have more information than all the other methods have. And this is just a comparison that shows the predicted the predicted coronal hole masks for the individual images. So for all the SDO channels that you can see here. And the last part here is the line of sight magnetic field. And that's pretty interesting, because when you look at this, where's the coronal hole, right? You can see it in 193 here. You can see the coronal holes pretty clearly. But when you look at the magnetogram, it's pretty hard to see. But neural networks are really good at capturing complex relations and can extract information even from this complex data. And even in this case, they can extract certain coronal hole boundaries. On the other hand, this is also probabilistic. So this means instead of getting just like points that are labeled as coronal hole or no coronal hole, we also have an attached certainty for the model. So the model will give us a certain classification value. We then finally take a cutoff. But we can see, for example, here, when we look at these regions here, it's kind of really difficult to say which parts are still part of the coronal hole and which part are kind of like bright points or other structures that are inside of the coronal hole, or like outshining effects. And in these cases, the model will give us some like more fuzzy structures. So this is kind of one of the upsides, is when even if we have a noisy data set or like a data set is not perfect, the model usually like tends to predict something with a lower probability score, and we can identify it from that. Okay, and then we have modeling. Only one person was saying modeling, but this is actually one of the biggest, like a really good point here, because that should be one of the most reliable things, right? Because what are coronal holes? Does anyone remember what I was saying in terms of the magnetic structure? Exactly, yeah. So they're a signature of open magnetic fields. So when we apply a magnetic model to this, a magnetic extrapolation, we should immediately see where the corner holes are. And this is partially true. So you can see here also, this is, so it's like a pretty old paper actually. It's like helium observations that we have. So those should represent kind of corner holes that we see. And these are the input magnetograms. And this is a extrapolation and then basically truncated at the top. And then we compare like the, where field lines are open. And that outlines basically the corner holes that we see here. And what do you think is kind of like the problem that we have with this modeling approach? Like, why is this not as successful as any of the segmentation algorithms? Like, the reason for this is it's a simplification, right? So usually the model approaches can't capture the full complexity of the underlying physics, same as the neural network can only capture like information from the data. So like this trade-off basically means that we can't replicate the sun exactly, and that leads to this deviation. That's where data-driven methods outperform basically. Okay, and then we have also way more classifications. And after that, you can tell me which one is better than the other, or like one is better than the other. But this is one paper. It's not on coronal holes, but this is on solar features. And what they did is kind of they created patches, like cutouts, right? And then they classified them into different categories. So here you can see those are like flare ribbons, prominences, and so on. And they label the individual images, like they manually label them, train the neural network on this task, and then can basically apply this to a larger data set where they can label all kinds of features that are in the image. So the same thing could be also applied to coronal holes, for example, where we basically take like a patch, and then we ask, is there a coronal hole in there, or is there no coronal hole in there in this patch? So what is the advantage for the classification? What is the disadvantage? Does anyone want to comment? What do you think? Like, what amount of information do we get from a classification? If we get like a single output, coronal hole in there, yes or no, right? Like, what is the amount of information? We just know there is one, right? It's a binary information that we have. But for segmentation, what do we have for segmentation? Exactly. So we get like the exact value, kind of where the coronal hole separates. So this is like really the information that we need in the end. It's also like the area information that goes into all the other modeling applications. Okay, let's see. Okay, we are doing good on time, I think. Good. So this one is a bit different because it's not about classifying features, but it's rather about like a kind of different approach to address recent challenges that weren't possible to address before. And this is about basically the idea of creating virtual instruments. So let's face this challenge here. What we want to have are spectral irradiance measurements over multiple solar cycles. And usually that would be great, and we would have that by now, if it wouldn't be to this malfunction of the MAX-A instrument on SDO. So from in 2014, we basically lost from the EVE instrument on board of SDO, the MAX-A part of it. And after that, we don't have any more observations from that. So what do you think? Can we replace that instrument with machine learning methods? And how do we do this? Should this be a classification problem, a regression problem, segmentation problem, or a data transformation? Or should we use modeling? Okay. Okay. Yeah, that looks good. So answers are coming in. We have kind of a tie between data transformation and modeling and simulation. Okay, a bit more data transformation right now. So, so 11 people were saying data transformation. 9 people were saying modeling and simulation. So what would be, does anyone want to comment what would be for a data transformation problem, what would be like a potential input that we could consider. So the output is kind of clear, right? What is our output in any case? What do we want to replace? Sorry? Right, it's an irradiance measurement, so it would be a single value, like the integrated value, so it would get like a time series of irradiance measurements. So this is kind of what you see up here. Also, like at a single point in time, the individual measurements that we get. So exactly, so for any case that we do, right, that's what we want. That's the output. The question is, how do we get it? So this instrument is located on SDO, right? And it was active between 2010 and 2014. And when we look at the spectral relation between the MAX-A instrument and the filtergrams, the imaging instrument, we can see that there's a good correlation. So what could be a potential input for this to train the model? The images, exactly. So since there's a relation in terms of spectral band coverage between AIA and the MAX-A instrument, we could just use the images as an input and estimate the spectral irradiance from those images. Ultimately, there's all the features in there, and the model should be able to recognize certain features, patterns, and relate them to the actual irradiance measurements across the individual spectral lines. And more importantly here, we have also like a pretty good coverage of those images across like the spectral bands across this entire part here. Right, any ideas on modeling and simulation? Anyone have a clue? Has anyone worked with differential emission measure before? Yes? Or the yes over there. Can someone shed light on this? What could we do with differential emission measure and this one? Any ideas? Yeah, maybe. But otherwise, I'll go ahead. That's also fun. Do you want to? Do you want to reveal? Okay.
So the differential emission measure, if you guys don't know it, is kind of like a measurement of how much plasma you have between the sun and you and its temperature. So if you're going to do this modeling, you have to try to get a sense of how much plasma and which temperature so that you can synthesize a spectrum of irradiance when you integrate over the entire star. So that will be the modeling component. Yes. Well, okay. It's a monotonic relationship between density and temperature and your intensity.
Thank you. Yeah. Yeah, that would be one application, but I also don't go into more details here. But let's focus on this application here because it's also a nice relation to basically basically a simple regression, to a linear regression actually. Because what the authors were doing is kind of like when we go back and we look at these relations here, we could also think about that between these channels that we have from the filtergrams. So if we take just like the mean values of the channels, there could be just a linear relation between what we observe in the filtergrams in UV images and what we observe in the spectral bands of the irradiance measurements. And this is exactly what the authors did here. So we just ignore all of this down here. So we don't care about that. But we focus on the top part here. So they use the AI filters as input, and then they just compute the mean and the standard deviation. And then they feed this just in a linear model. So same as you've seen before, right? And from this linear model, this is just like optimized to match the outputs of the MAX-A instrument. And right, so, and basically this is kind of like already a really good assumption. Like just a linear model is like pretty much sufficient to do this. And the only second aspect that they use here is to use also a convolutional neural network, which basically extracts features, but this only adds an additional part to this. So what they're doing is kind of they take this simple linear relation and then they just apply perturbations with a more complex model to it. So it's a very nice combination where you can see that with a smart design, you can basically combine like the simple approach, which can gives you reliable results with little data, and the more complex approach, which can improve those results with more complex data. And yeah, I mean, like what they did in this paper as well was basically to show that they can do this for like with an error of 1.6%, which is great because that means we have a good replacement of the max A instrument. And so the idea is clear, right? So we have the input images and the max A measurements during the time while the instrument was running. And after it died, we can still use the filtrograms as input to continue the series. So it replaces the instrument and basically serves as a virtual instrument. Okay, I think I'll skip this part here and just go to the flares so that we have some time to go through the physics-informed part as well. Right, but that will take like half an hour for the physics-informed part. Yeah. Okay, so solar flares. I have to address this here because this is like one of the big challenges and one of the problems that is frequently addressed. And you frequently will hear it addressed as the holy grail of space weather forecasting because it's so difficult to get, but it's so important to get as well. So first of all, when we look at flares, it's a very complex physical process that is going on, and it's very a rapid process as well. So we have basically little observations in terms of like what is actually covered of the solar atmosphere. We only have a sparse set coverage of what we have. And we want to predict like the entire physical process from this. And ultimately, we want to know when those flares are happening because those are the trigger like basically the entire chain of space weather effects, and it's the one event that basically as soon as it triggers, we have this huge amount of intensity that is being released at a single point in time, which can have immediate effects on Earth. So that's why we're particularly interested in this problem. So question back to you. What do we pick? Is this a classification problem? Is this a regression problem? Segmentation, data transformation, modeling? Oh, sorry, I think I need to advance the slides for you. Okay, I see a lot of classification coming in, and I see also modeling coming in. A bit of segmentation as well. Okay. Yeah, I think for the machine learning and deep learning community, it's the classification task is the go-to. Of course, there's modeling as well, and there's a broad community all about modeling, and we'll hear a bit more about this potentially later. But for the machine learning community, it's kind of classification. Classification because we have different flare classes we want to forecast, and we want to have, in particular, this probabilistic forecast. It's a very challenging problem. So predicting like a regression problem that would predict like strength of a flare, for example, as a continuous function would be too challenging for most cases. So people rely on going back to classifications. So it's really difficult to cover like the whole field here because there are multiple different applications, but I just wanted to highlight a few which are kind of interesting here. But this is one of the first ones that came out where they were basically using a simple classification task without using actual images as an input, but just using sharp parameters as an input. So sharp parameters are extracted from active regions, and those give basically information about different magnetic configurations in the active region. So what they were doing basically, they included the set of parameters and then ran basically a prediction model on this. And the nice thing about using something simple as like just a support vector machine for this, which is the model that they used for this, is that this also allows to better investigate what is going on. And from this, we can also see, this is what they provide here. So you see the different parameters. And then they're ranked according to their score, where they basically rank like the highest importance for the model to the lowest importance of the model down here. And that gives information about what the model actually considers as important feature for a flare to happen. And that can give us important information. And for example, things like having a polarity inversion line or other magnetic features are always ranked high. And that's kind of a nice feedback loop where we basically use physical knowledge to train the model, but also the model returns us information about what are the relevant physical parameters or which of those are not important at all. We can also use this in a more complex setting. It's also classification. So, but with a convolutional neural network. And I just picked this one example here, where they basically use a magnetogram as an input. So you can see this here. It's really nice if papers describe it like this, right? Because it's all clear from the beginning what is going on. If it's described like this, that's the image that goes in. That's the architecture that is being done. And then there's the output at the end, okay? And that's just a classification between flare is going to happen or not. And here they are forecasting based on a single magnetogram, the flare occurrence in 6, 12, 24, or 48 hours in advance. So before we talk about this in a bit more, let's have a look at another interpretable flare prediction system, which goes in kind of a different direction. So rather than using like more information as input kind of, what the authors here were doing is basically to look at spectrographic data. So they were basically looking at line profiles. And then they were using, similar as other methods before, like an attention mechanism that gives you attention maps and like shows you where the model what the model is focusing on. So basically here in those plots, you can see individual spectral lines. Those are used to predict like flare occurrence, and they have like a data set that they have manually labeled for flares that are going to happen. And then afterwards, they can basically go back into the model and study which features were relevant for the model to predict a flare occurrence. And for example, here they found that flows, broadening, and asymmetric profiles are always like triggering the model. And this is kind of interesting here that we can basically go back into the model and examine kind of which features are the most relevant ones. Okay, and then the last part that I want to address here, which is about solar flares, is actually when we look at those tasks that people try to solve. Might be a good idea to take a step back and think about which task we are trying to solve. So of course, the operational side tells us we want an operational flare forecasting 48 hours in advance. Tell us if there's an X-class flare happening in 48 hours. So let's have a look at this here. And then this is basically the go slide curve. So we see basically flares as spikes here. And this is from a magnetic model which shows the energy that is being built up in this active region here. And when we go back to 1 day before and 2 days before, we see that there's barely any active region there before. So how is the model going to know that there will be a flare if there's barely any energy yet injected into the system? So do you think a neural network can predict like this evolution like 48 hours in advance just from this? Maybe it can be statistical, like that it says there should be a flare occurring at some point, but it's probably not picking up any features. So it would be a purely statistical approach, right, in that regard. And the interesting part about this, when you look at this in the literature, is also when you see like statistics, you'll get the highest performance, of course, for the 48-hour forecast. Why? Why do you think it's like a 48-hour forecast typically performing better than like a 6-hour forecast? Any ideas? What could be wrong? Like from the definition. Let me clarify. The 48 hours forecast means a flare could be happening from now, any point from now to 48 hours in the future. And the 6-hour forecast from now to 6 hours in the future. So you have a much longer time window, much more range for any potential errors, and that kind of improves the performance. So it's always good to question which metrics are used, how is this evaluated, and how is this done. Yeah? Okay, so last thing here, and you don't need to vote for this, because this is kind of where I want to transition, because this is about coronal magnetic fields. And basically the science application here is that we have only measurements of the solar magnetic field, like spatial measurements, not just a single point in space. from the solar photosphere. But actually, when we look at this, you can see this is the magnetogram where we measure the magnetic field. And then this is the EUV corona. And all of this is structured by the magnetic field, right? But it's just an outline of the magnetic field. So it's no direct measurement of the magnetic field. But it drives the entire dynamics here. And when you compare the EUV observations to what we have in the magnetograms, we can see this vast difference in terms of what is actually going on. And most of the dynamics are happening all the way up in the solar corona. So we need some way to understand how basically the magnetic field evolves in the higher solar atmosphere. Okay, so any ideas how this could be addressed? Do you think, let's just talk about this. What do you think? Classification? Like we have a magnetic field at the photosphere. We want to learn what is the magnetic field higher up in the solar atmosphere, in the corona. Could this be done with a classification? Not so much, right? How about the regression problem? Like how would you translate this? Segmentation? No. Data transformation? Depends, yeah. But what would be the data for the data transformation? Do we have measurements of the corona? Of the coronal magnetic field? Sometimes, sparse measurements. So definitely not a large data set. Too little to learn like a proper relation. So I think the only viable option here is modeling. And so far we were only talking about modeling from the side, from the viewpoint of classical methods, solving partial differential equations. And frequently people, like a lot of people were responding now with modeling approaches for all of the approaches before. And all of them are also addressed with modeling. But can we do modeling as well with neural networks? That's the big question, right? Can we use modeling and simulation methods? Yeah. Yeah. Yeah.
That kind of convolves density. White light coronal picture.
Right.
I'd love to see us kind of take how that compares. Challenging problem, but now we are beginning.
Yeah. Yeah, I totally agree. It's also like a really complex system of observations that we have, a complex image formation process that's really difficult to understand and difficult to model. That's kind of the big challenge for our community, to understand how different data is like being generated, kind of what is the underlying process that leads to what we observe in the 2D images. Andres, yeah?
Just for everyone's situational awareness. So what Robert is going to get into is what I personally think is one of the most exciting directions in which heliophysics is going. But besides modeling, there is also, I just wanted to, just for completeness, to mention that the generative, there is a possibility to address this using generative processes. So, and maybe I will talk a little bit about that on Monday. But that is also an alternative that Robert is not going to go into, but it is possible, it's available to all of you if that's a path you want to pursue.
Exactly, yeah. And that's probably an advertisement for Monday, right? Yeah, yeah, but I skipped here for most of these applications. I skipped the generative approaches, which are of course very powerful, but you don't know them yet because there wasn't a lecture yet about this. So we'll move this whole discussion to Monday. Okay, so this graph here, that's kind of really simple. What do you think? All of what we were doing so far, apart from the last one, where is this located? Like all of the tasks that we were looking at in terms of data and understanding of the physics, like where are we kind of like located? Do you think, let's say, for example, the coronal hole detection, do we have there big data, some data, or small data? Big, yeah. Okay, yeah. We're in the big data regime for sure, right? 12-second cadence, 4K by 4K images from SDO-AIA is a lot of data that is coming in, yeah. And and you mean for the magnetic fields right now? Yeah. Right. Perfect. Where are we with the magnetic field measurements? Here, right? The only thing that we have is measurements from the photosphere. But what do we have? Let's go back to the coronal holes first, for example. How much physical understanding do we have between this is like the image that we have, and what is the physical process that forms that image, like just from this representation? Not too much, right? So it's kind of like located here because we are dealing with imaging data, and the model that we are training with is kind of like stupid in that way, right? It only learns like thresholds or boundary conditions, but it has no real perception of like this is like a three-dimensional object. Probably. It's hard to tell what the model figures out. But we are probably like located in this regime. Okay, so about the magnetic fields. We have no in situ measurements. We have only photospheric measurements. But what do we have? What do you think? Lots of physics. So we know how magnetic fields work. We know how MHD equations work. And this is exactly the regime that we want to learn more about, which is where we can use AI to learn new data from the small data by using the physical constraints. And there's also this regime in between where we have some physical understanding that's not complete, but also some data. So we could also combine that to learn more about the underlying system. So that was just a break in between. So we'll switch to this one here. And I just want to give you like just the difference between those two approaches here. So when we think about this for this simple example here, which is like this harmonic oscillator, right? The idea is kind of we have points sampled along this function, but we basically cut it off here. And then we can treat this like as a machine learning problem where we use those points as an we try basically to learn based on these data points how the function evolves. So if we just do this with a supervised training where we set up like an arbitrary neural network, like could be a small neural network, for example, and do supervised training with this, what we will get is kind of like fit like this. So it will just fit the points. And then once we have no data available, it just like collapses away and it doesn't capture like the underlying physics. So this means it's of course very little data. So the model has basically no chance to learn the underlying physics from that little data. But on the other hand, when we have an understanding of how this harmonic oscillator works, and we can basically use this equation here as part of the modeling process to learn just the free parameters based on the data. And with this, we can get like an exact fit of the function. So by understanding where our data is coming from and the physics where it is coming from, we can basically get a much better estimate about the data that is produced from that. Yep. Right. No, I mean, like this is pretty much converged. Like all of these, both of these models were trained till they converge to a certain point. It's really like the data limitation that brings this up here. But it's a good point because this also shows you that while we are potentially like faster with the training with the supervised approach, it's much more expensive with a physics-informed approach. We'll have a closer look at this, how this works in a bit. And just to highlight this here, this is like the super simple image that I want to give you. And this is basically about the way we do supervised training is just this simple input-output scheme, right? We have an input, we have our output, we compute the difference to our target, and we start to optimize the neural network to find this function mapping between the inputs and the outputs. On the other hand, we have physics-informed neural networks. So this is kind of what we want to do, where we basically combine physical losses and observational data and integrate them into one model. And if there's a good point to forget everything about what I told you so far, now is a good time, because this is very different from supervised training, okay? So if you want to take a step back and don't think about any deep learning applications, this is the right point to do so, because this is very different from all the other concepts, okay? So the way this works is basically by using the neural network as a representation of the underlying function. So basically what you can see here is kind of a partial differential equation that we want to solve. So this is our physical model. And what we're doing is basically we create a function of the spatial dimension here in this case of x. And the function that we're modeling is u of x. So the neural network serves just as a function representation. And then we can use this function representation to match certain boundary conditions, but also to match the physical model. So how do we do this? And the way that we do this is with automatic differentiation. So once we have this function approximation, we can use this concept of automatic differentiation to compute the derivatives of this function with respect to the inputs. I think I have it on the next slide, right? Yeah. So here is like a more detailed overview of how this works. So just to review how this ties into this previously mentioned chain rule computation of backpropagation. So we use exactly the same concept here, but use it to construct derivatives. And the way that this works is by basically having like here this super simple neural network, right? We have our input x, and we have the output of the neural network, which is basically takes x as an input and produces like the corresponding value at that point, and then represents the function u of x. So if we want to compute now a derivative of this function u of x, we can basically just unroll this neural network and basically take the derivative of the output, which is the neural network itself, with respect to the input coordinate x. And then by just expanding this term with the chain rule, we basically get like the derivatives of each single parameter. So the advantage that we have here is that we have a fully differentiable function. And as such, we can compute smooth derivatives of that function with respect to the input values instantly. Okay, I think this will be clearer once I get into the details about how this is actually applied to the magnetic fields, because then we have a practical example and you will understand how this is actually useful and how we can use this. But just here, like as a quick outline, it's basically supervised versus physics-informed neural networks. So everything that you have heard so far about having certain amounts of having data sets, training set, validation set, learning a general task, learning a specific task, this doesn't apply to pins. So for physics-informed neural networks, we're only interested in solving one specific task only. And this is the important thing to remember here. So where could we apply this? So for example, for PDEs in heliophysics, we have the magnetohydrodynamics equations. And those are the set of equations that basically enable all of these amazing simulations that we get of the solar atmosphere and solar interior and everything else that is like driven by magnetic fields in our heliosphere. So this basically provides a framework, like physics-informed neural networks provide a framework for us to do this. So this is a comparison just to simulation methods where this needs to be placed on a grid, right? So we place every point on a grid. We have a simulation volume, and then we compute finite differences to estimate the gradients. But for physics-informed neural networks, we don't need to provide a grid. The neural network serves as a function representation of the simulation volume. And as such, the difference is that while, and also like in contrast to other approaches, physics-informed neural networks are very similar to PDE solvers, to simulations. So what we're actually trying to do is to run simulations. Okay, let's jump to the heliophysics example. Yep, sounds good. I'll just go through the magnetic field application with you, but I will also let you know that there are way more applications that can be addressed with this. But like just going back to the original problem that we had, we can look at this. We have the magnetic field observed in the solar photosphere, and we want to understand how the magnetic field is being structured and built up in a solar corona. So basically, just based on the observations from the photosphere, we want to learn, or like we want to estimate the coronal magnetic field. And one way that this is done, like for classical approaches, like modeling approaches, is to use force-free magnetic fields, or specifically nonlinear force-free magnetic fields. And here it's actually kind of a simple application of this, and this breaks down the full set of MHD equations to just two equations, where we have the divergence-free equation and the force-free equation, where J is curl of B. So basically we have those two equations, and what we want to do is described here. We have our input data, which is the photospheric vector magnetogram. And then we have here above this, the box, where we want to estimate the magnetic field. So the way that we address this with physics-informed neural networks is to actually, just for the single case, to make the neural network a representation, a functional representation of the magnetic field B. So this comes really down to the essence of neural networks being general function approximators, right? It can be anything. And in this case, it's the magnetic field B. So what we take as an input are the coordinate points that we basically pass into the neural network, and the network just maps it to the magnetic field vector at the respective points. So for the boundary condition, this is straightforward, right? We know the boundary condition, we know the values there. So the only thing that we do is basically we go here, we compare this value to what we have in our input data, and then we optimize the network to match this boundary value. But what we actually want to do is we want to find the solution to the system of partial differential equations in the rest of the simulation volume. And the way that we do this is by basically passing random points, like sampling points in this volume where we want to have these equations satisfied, and pass them through the neural network. And then we compute derivatives of the output values with respect to the input coordinates using this automatic differentiation. So this gives us automatically smooth derivatives that we can then use to construct our partial differential equations. And then we can just optimize the network to, like, step by step, to minimize the residuals of the partial differential equations and the boundary condition. So what we have in the end is a solution that satisfies both the boundary condition, or like approximately satisfies the boundary condition and the physical model, which gives us then in the end our magnetic field solution in the simulation domain. So this is how this approach works. Maybe I'll pause here quickly. Any questions about this? Because I think this is kind of critical to understand how this works, and I hope that this example makes it kind of clear what the aims are and how this is being solved. It's kind of understandable? Any questions? Yeah. So basically, what needs to be done with all of these approaches is first to test them. And what we did here with this study is basically to apply this to an analytical solution. So we basically construct, like from an analytical field solution, a magnetic field, and then we only extract the bottom boundary, and then we apply this approach to this. And what you see is basically here, this target solution, and then this is what the neural network provides us as output once we apply the physical model and start this optimization procedure. And most importantly, this is a configuration that was also used in the previous comparison study of 6 methods. And the physics-informed neural network approach provided the best results out of all of the other 6 methods. And then we can also apply this to observational data, for example. So this is kind of what you can see here. And then we can estimate how the magnetic field is structured in the solar corona. So this gives us one estimate. And when we compare this, we can see basically this good agreement between current carrying fields in the solar corona and the bright loops that we observe in EUV. And you can also see, like here, this is like a structure that becomes visible briefly before the eruption, and this is already in the model available before. So this could be kind of like, when we think about flare forecasting, could be already a precursor for a flare, for a potential flare eruption in the future. But also very interesting here is kind of the way that we can use this to estimate and investigate like the energy budget of active regions. So this is kind of like the primary challenge for for flare predictions and flare forecasting is to estimate how likely an active region is to flare. And the primary component for flaring that determines the flaring of an active region is, of course, the total amount of energy that is being stored. Otherwise, there can't be any energy released. So approaches like these can basically give us an estimate about how much energy is available. And this can be done with this modeling approach. So here you can basically see this is like the flare occurrence. So the spikes here relate to flares. And you can see this large flare here. This is the X-class flare that we have. And we can also see this in the free magnetic energy of this active region, that this is nicely resembled by the model, that we see this energy release also in our data. And if we would just compare this with magnetograms on the other side, there would be no trace or like a very small signature of this flare event, but we can see it clearly in this modeling approaches. So this is kind of really where physics and data combined can give us more information. And then we can also investigate this further and basically identify regions where flares occur. So you see basically, even though it's like a fully like a modeling approach, we also have like a ability to extract more features. We definitely have more ability to extract features from this. I think, is it fine if I just go through this last part? Because I think this is kind of, so it should be like 2 or 3 minutes, okay. Because I think I'll go through this and then I'll stop and bring you to the summary slide. But basically, these magnetic field extrapolations and also the magnetic field extrapolations that we were doing are all similar to existing methods, right? So you could ask, well, we can already do that. So why would we use now artificial intelligence for that? Why would we use physics-informed neural networks for this task? And the answer is basically what we used here as an extension of this method, which is this high flexibility. So physics-informed neural networks are particularly good in terms of integrating noisy data and incomplete physical models. So they can intrinsically find the trade-off between the data that we put in and the model that we try to match. And this works particularly well. And one example of this is basically this here, where we tried to advance this forward, where we use chromospheric magnetic fields. So when I told you the only measurements that we have of the solar magnetic field are from the photosphere, I was actually lying, because we also have measurements from the chromosphere sometimes. And this is one example where we have chromospheric magnetic field measurements. But the problem that we have with these observations is similar to what we have with EUV observations. We look at 2D images, but those are not 2D structures. So for the photosphere, we can maybe say this should be approximately flat, which is also not true. But for the chromosphere, we can definitely not say that those observations that we get correspond to a flat surface. So we actually need a way to interpret our data as a 3-dimensional structure rather than a 2-dimensional object. And this is kind of what we did here. And this is a physics-informed neural network approach where we use additional decorrugation. So kind of what this does is like simplified here. We have magnetic fields as an input. We map them into the neural network. This gets information about each point in terms of X, Y, Z. And then it has the flexibility to remap this surface to a different height surface. And then this is used in the same way as before to solve this problem, this boundary value problem that I was talking before. Right. And how does this work? How is the model, like we don't have the information about the height distribution, right? There's no reference. How is the model able to investigate this? And the answer to this is basically that this is a coupled system. So meaning that this observation defines how the extrapolation looks like. And basically this information defines the difference of the reconstructed magnetic field. But on the other hand, the extrapolation itself informs where the magnetic field is located in 3D space. Okay, I'll just show this one real quick. This is about basically where we applied this method then to simulated data. You can see basically those are 3 slices that are extracted from an MHD simulation. And this is the corresponding height. So when you look at the images, I don't see any height information there, right? So if we just look at this, I would say this could be flat, right? But there's actually a significant difference. So this goes into the megameter range where we have like a remapping of these height surfaces. But just applying or like using these parts as input, we are able to reconstruct the magnetic field. and the height information as well. So this gives us also the height information of each of those pixels in these magnetic field measurements. And most importantly, when we include additional information, our extrapolation results also get better. And finally, we can apply this to observations. And this is kind of a comparison. We can see kind of like what the difference actually is. So when we apply just photospheric magnetic field extrapolation, this is kind of an extrapolation result that we get, where we get like sheared arcade, kind of low-lying loops. But once we include the chromospheric magnetic field measurements, we get this information of magnetic twisted flux ropes in the solar atmosphere, and we get like those elongated, highly twisted structures that have way more information about flare occurrence for us. And when we compare this to the observations, we can also see that there's a filament there. So this is a nice match here as well. Okay, I'll skip the last part. So I made some. Just in case you were like super fast with the initial introduction. So, but basically, those just to review this really quick, in the end, physics-informed neural networks, they are not only applicable to magnetic field data, but they are applicable throughout in the multiple different applications. So we used them in the past as well for spectropolarimetric inversions. We use them for tomographic reconstructions. There are applications for electron content estimations. They can be used for CME tomography. There are MHD models or like initial MHD models with physics-informed neural networks. So this is like also a growing field that's very interesting because it basically combines both the modeling expertise and like the AI expertise. And this is like one of the methods that can really benefit from the recent trends in technological advancement, where we can really use this high performance computing power to solve partial differential equations in a more efficient way. So just to conclude here, so I was talking about supervised training in heliophysics. I hope I was able to show you that there are very interesting applications out there for handling different tasks, and there are lots and lots of opportunities and still open challenges that can be addressed by machine learning methods in heliophysics. Those methods are extremely well suited to handle large amounts of data. They can be used for event detection, forecasting, feature extraction, and also for advanced data processing with abilities that we haven't had before. They are also particularly important for operational use, where this is basically all of them are like most of the supervised training methods can operate in near real time. And I hope I was also able to show you that physics-informed neural networks provide like a new state of the art in terms of data-driven simulations, and that they have lots of potential for the future. And with this, thank you.
Thank you for the talk. I was just confused. The automatic differentiation is the same as backpropagation, right?
Yes, just a matter of what you're backpropagating. So usually you would, for the optimization, you would basically compute the derivative of the loss with respect to the individual parameters in your network, right? So you would compute basically like the graph that gives you information about how do you need to update individual weights in your neural network to basically have the gradient that optimizes like the total loss in the end. While for this one, we only compute the derivative of the output value with respect to the input coordinates. So actually, for a regular supervised training, you would never compute this derivative, the very last one, because you wouldn't be interested in how the input would kind of change your output in that sense. But this is kind of like exactly the same machinery basically that computes it, and it works very much in that way. It's like in the code that what you're doing is kind of you call one line and say compute the derivative, and since this is all like handled in the background, this can immediately benefit from computing this directly. So also when you compare this to like more advanced like mesh-based methods with finite differences and so on, right? This is the big challenge that they are facing, is kind of how to efficiently define a grid, how to compute the derivatives in an efficient way, what is the proper stencil that is being used for those derivatives. And for physics-informed neural networks, you basically just have, this is my output, give me the derivative. And this is kind of the big advantage there.
Can I ask one more? Okay, so it seems to me that to use pins, we need an underlying model as well, right? So is the advantage just that the traditional numerical solvers are slow and pins would be fast once you train it, or there is other advantages as well?
Right. You were saying an existing model, right?
Yeah.
Right. This is the point here. No, it's completely independent. So you can see it as a separate solver method. So it's not dependent on any other approach that we were using before. So when I was saying like, forget everything about supervised training, right? For this application, not in general, right? Just for this last application for pins, that's probably the best way to communicate it. Because it's significantly different from supervised training, because for supervised training, you're always dependent on having your input and output pairs, right? You need to have both of them available. So you would need some predefined, like some model that already computed that quantity. But with pins, you can actually explore new data. So this is kind of the real advantage where this comes in. And this is basically enabled by solving the physical equations. So like as any other numerical solver solves problems, pins do it in the same way. They just solve the system of equations, the boundary condition, solve the boundary value problem, and you get your solution, which is completely independent of any other solver. But in terms of speed, that's also a good point. When we compare it to supervised training, they're like extremely slow because you would need to train this per example, right? Every new magnetic field that you want to estimate, you need to start from scratch. It's one neural network represents one magnetic field that you're extrapolating. For supervised training, you would have like a general mapping function and you would learn it, but you would be limited to what it can achieve, right? Based on the data set. With pins, you can get better than what your data set, than like a supervised training could be. Like you could, like with pins, you can basically exceed previous methods. While with a supervised training approach, you will be always tied to the data that you have available or like other models that have it already computed before, and you can just like increase the inference time, for example, for this. Yeah. But this is, I would say, this is like the biggest advantage for pins that they are able to advance forward. Yeah. Yeah, I think the mic is also there. Yeah.
I just wanted to say that one of the things that to me has been the most exciting discovery of my last 2 years is that almost any mathematical sequence of almost any sequence of mathematical operations that we use in heliophysics is differentiable. So you can backpropagate through anything. So pins are like in the context of your question, you know, if you're going to be using pins, then it's a completely different thing. But you could backpropagate through anything, optimization steps, integration, numerical integration steps. You can coordinate transformations. You can backpropagate to things that most people don't even think to backpropagate through. And so that's just the clarification that I wanted to make. It's not a pin, but you could backpropagate through a solar wind acceleration model. It's not a pin, but you could backpropagate through a surface flux transport. It's not a pin, but you can backpropagate through a differential emission measure optimization. It's like, you know, and I'll talk maybe a little bit more about, but if there is something I would like you guys to remember is that, like, you can backpropagate through anything that is differentiable.
So regarding the coronal field extrapolations, do you need for the ground truth some preliminary three-dimensional distribution of the magnetic fields, let's say acquired from the 3D MHD simulation? And if then you build your functional representation based on that, would it be then different from the force-free extrapolation or not?
It's like it's completely independent. Let me just pull up the slide after I'm through those 20 slides here. Okay. It's really just the boundary value problem, and this is really the starting point, right? Like this is all that we have is just this single magnetic field at the bottom boundary. So was your question about the dependence on the nonlinear force-free solution? You mean like in terms of the model itself or in comparison to other models?
Just to clarify, yeah. So you were mentioning that you use the 3D MHD results, and I was wondering
I
if
see,
you're
I see.
using.
Oh, this is like for this example here. Right, that's a good point to raise. So really just to clarify, what we're doing is kind of, or why are we doing this is similar as with an analytical field, for example. We just use this as a test set, right? We usually don't know the solution of the magnetic field, but we need some way to actually show that this method works. So the way that we're doing this is kind of to use this for a self-consistent MHD simulation. And basically this simulation has already the provided results, and then we extract synthetic observations from that, feed this into the method basically, and the method provides the magnetic field solution from that. And then we can compare this to the ground truth of the MHD simulation. So it's kind of what you see here is kind of, this is the ground truth that is being extracted from the actual simulation. And this is kind of, those three images are kind of the only thing that go into the neuron, like into the physics-informed neural network. And this is what we obtain after the reconstruction of the magnetic field as an output of the magnetic field. So those are completely independent of each other. So like this information is completely hidden.
Thank you.
Maybe I can like say one more thing about this, which is probably a good point here to raise is, so the MHD simulations are like a realistic, like very realistic approximation of the solar magnetic field. So why are we not just using the MHD simulations, right? Why are we doing the extrapolations, for example? The difference is the MHD simulations are self-consistent simulations. So you start from an initial condition and let the system evolve. You have after that basically very little handle on actually incorporating any additional observations. And what we know from our physical models is that while we can study the MHD equations in a large amount of details and in a huge complexity, they don't replicate the sun exactly. So this means there's some missing physics. And what we're trying to do is by building on pins to have basically a better handle on including data constraints. And this is like the way that we move forward with this is by advancing the physical models, but also incorporating more observational data constraints to actually match better the sun. So this is kind of the ultimate goal, to better reproduce what is actually happening on the sun and to have a simulation that can account for the missing physics that we have in our MHD models.
So if I remember correctly, then you mentioned in a slide that you need to train your physics-informed extrapolation model every time for a new magnetogram. Is that right?
Yeah, it's you were saying it's trained for every every single magnetic field that we put in. It's trained from scratch, right? Like we start a new model basically for each individual sample that we're observing. Yeah, so this is kind of like where it becomes like definitely less computationally efficient, right? If you would think about it, like you have like your known solution of the magnetic field, you have your boundary condition. You could just say we feed in the magnetic field and we estimate the full 3D field from that, right? And there are approaches that do this already. So there are, this goes into neural operators kind of in this regime. This can be also done, but you will be always tied to the ground truth data that you have. So the method will be only replicating at best the existing methods. It's just a computational effort there. In this case, it's computationally slower, of course, because you need to train every time from scratch. But you basically solve similar to any other solver method. Yeah.
Can I ask how many times slower it is? Like, is it just several times or tens?
I think the proper comparison here is to compare it to other solvers that have basically the
Yes.
same task. And in this case, it's even 3 times or more than 3 times faster. Like what we did in our initial study with this is basically to show that we can make efficient use of this once we have this encoding. So like this time sequence here, which has like all of these individual data points, was computed in less than 10 hours of total computing time. And usually for existing nonlinear Force-free extrapolations, you would take like 3 to 6 hours or something for a single snapshot extrapolation. So how do we do this? It works in a way that we basically make use of this representation. So since we have already like an initialization of the magnetic field, we can just swap the boundary condition and then retrain. And that's very fast. So then we are like in the range of a few seconds for the training, and then we can compute this whole thing in like less than 10 hours.
Thank you.
I wanted to ask a question.
Well, it's not on pin.
You've got, this is a meta question. So you've got data, right? From a lot of different sources. You've got the ML algorithms. You've got MHD simulation, right? How big is your collaboration? Like, how big is your collaboration network? Right? Surely you're not. So I guess surely you're not an expert in all of these, right? And so how much time do you spend working with other people and getting input from them on this?
Right. Like for me personally, right?
Yeah.
Yeah, I think that this is like, especially like from the modeling side, it's this collaboration which is like really, really important here, because like when I got started with the extrapolations, for example, I of course had like expertise in how to set up deep learning systems, machine learning methods, and so on. But I really needed like the expertise coming in from also other people to think about like how to properly set up the task. What is like the state of the art right now? Like especially magnetic field extrapolations are kind of difficult, tricky topic, and to learn basically what the community is already doing and just advance on that, or like use like already successful approaches and have someone who actually did this before is kind of extremely valuable, of course. So like lots of collaborations there, and also from the physical perspective of like even other applications that I was working on, like for example, like the coronal hole detections and so on. There was already, when I got started with this, there was were multiple people in my working group working on coronal hole segmentations and detections. So there was already a lot of expertise there, and it's always great to profit from that and to incorporate basically like both like the machine learning aspects plus the physical knowledge there. Yeah.
So how big is your contact list for?
I would need to check.
Other questions for
Should be-
Robert? Yes, please. Yep, you got it.
So back earlier when you were showing the some of the coronal hole work, and you had the panels that had the attention maps. I'm somewhat familiar with attention in the context of LLMs, but how did you use attention in that context?
That's probably, it's not the, like it's frequently used, like it uses the same term, but it's actually a different method. So let's see. The method itself is called GradCam, I think. Let's see, sorry, skipped it. Sorry, it's SolarWind, right? Yeah. Like for this one here, yeah. The method itself is called GradCam. It's also used for the other flare forecasting method. It's basically like that wouldn't impact the training at all. It's just a post-processing approach where this method is basically like scanning, like computing gradients forward and then like tracking down which parts caused like bigger spikes. So it's kind of an attention map. It's not sure. Exactly, yeah. This one, like the one on the right, actually uses a vision transformer, but that doesn't, didn't really show like as nice images as the one on the left-hand side here. So maybe also for the vision transformer, it might be more tricky to trace it with this algorithm in particular, but especially if it's like easier, like simpler models, it's a good way to probe this. Like for example, like this one on the left-hand side here, they basically used like a pre-trained model first and then added like an additional layer. They kept the pre-trained model fixed, and then basically just the last layer is like learned to adapt to the solar wind forecast, and then they use that layer to probe basically where those regions are. I think that's kind of the primary way that they did it.
Last questions? Going once? Oh.
I heard that to predict the time series, it was very common to use Gaussian processes. Is it, does it have something to do with machine learning, or it's completely separate field?
Gaussian processes in the time series forecasting regime?
Yeah.
I don't know. Do you want to comment? Yeah. Okay.